Well, today we are going to learn about generative adversarial networks, or GANs, G-A-Ns. They're used extensively in the area of deep fakes, and they're a lot more powerful than you think they are. At least that I thought they were when I first saw them. They can do just remarkable things. I've asked Glauco Amigo, who is on your screen. He's in the wave, Glauco. Okay, Glauco is from Spain, and you'll notice he has a slight accent. Okay, just a little bit of an accent, but a little bit of an accent. But since his English is a lot better than our Spanish, I've asked him to go ahead and speak in English. So he's going to talk about GANs. Currently, Glauco is a PhD student in our department. Previously, I don't know, some of the things he's done are just astonishing to me. One of the things is he spent 3 years in social work helping little kids. And that has to get to you after a while, especially some of these little kids that are troubled. He's a pianist. Man, that's something, you have a list of stuff you'd like to do in your life if you have more time. I would love to play piano. I wish I could go back. Do you still practice, Glauco, at all?
I play a little bit, like when I do laundry, half an hour a week or something like that.
Wait, you play piano while you're doing laundry? Do you take the piano down to the laundromat, or?
No, I go down to the laundry, and there is a community room with a piano, so I just stay downstairs.
Okay. So you go to the piano, you don't bring the piano with you. Okay. So that's really good. He worked in computer science and IT for a couple of years. I found out about him, and I recruited him here to come to Baylor, and I'm glad I did. He's doing just wonderful work. So Glauco, I'm going to turn it over to you to talk about GANs. And GANs are fairly new. How long have they been around?
They have been around like 7 years. The initial paper was from 2014 by Goodfellow.
Okay.
So, yeah. But there is a big development since then.
Yeah, so it's one of these things that took a little while to get off the runway, but now it's really soaring in terms of its applications. Yes. So that's kind of fun. Okay, go ahead, Glauco. You have, and thank you for putting this together. We all appreciate it very much.
Thank you. I appreciate the opportunity to be here presenting with you all. And I have a little disclaimer, is that many of the things that I include in this presentation, I use from slides that Dr. Lee and Don had shared with me and give me permission to share with others. But I added some other things, and yeah, I wanted you to know. Let's go and here it is. Yeah, I don't know if the audio is going to make it through, but these are my nephews from Spain. Probably some of you know this Reface app. I don't know if you are going to listen to the audio, but it was very fun to me to see. Can you listen? Ah.
We can't hear the audio.
You cannot hear the audio. I'm sorry.
No, we can't hear the audio. I'm sorry, but the head choreography is really impressive. I don't know how they did that.
Okay. With the audio is so good. I was to remove it from the presentation, but I'm going to let it there so you can watch it later if you want.
Okay, so we can see it. What are they saying?
Is this sound that I feel good? I feel it that.
I feel good.
Okay. Yeah, it's that song. Yeah. My sister sent this to me 2 days ago, and I say, oh, that's great. I couldn't stop laughing. I have a few more examples to show to you before explaining the GANs and everything else. Oh, here we go. This is this is a video. I'm going to play some portion of it. These are faces produced with a GAN. And it's a GAN that combines the face that it generates with another independent image to give a style to it. And here in the left, you see the controls, 4x4, 8x8, and so on. So the final resolution is 1000 by 1000, but they do it by stages, by different layers. We will see that at the end of the presentation. These all are not real faces. They are artificially generated. They are not real people. They are the product of a game of generative networks. These are interpolations that are possible with the GANs too. I'll explain them in detail how interpolation works with GANs. It's transitioning from one image to the other. Yeah, these are the same kind of networks applied to cars, bedroom, cats. These are also fake images. They are not for real. Yeah. This is when they change the low resolution layers of the GAN. The changes in the final pictures are big, as you can see here. When they change the middle layers of the GAN, they are not that big, the changes, but still significant. And when they change the fine styles, the last layers, the changes are just colors, and I don't know if something else was changing there, but they are more subtle. Here in the presentation, you have other resources if you want to check them. This is the same GAN. The GAN learns a model distribution. So when it generates fake faces, it can transition from one face to the other. And there is a resource here in this link that you can use by yourself if you want. So you upload a picture, and it finds the closest GAN generated image to the picture you uploaded. So I tried it first with this picture, the top left. I had glasses, and it didn't work very well. I think it was trying to put my glasses there, so it was scary. I didn't know if continue using the notebook or jump to something else, but I decided to give it another try, and this happened. I put a nice picture of mine, and but it was not well centered. My face is not in the middle, so it was a total failure.
You know what this means, Glauco? It means that in this world you are unique. There are no other faces that look like you. Okay.
Yes, I decided to put a big smile in my face and do it very clear. And yeah, this is much better. The last one.
Oh.
I can tell it's not me. I think it's very different from me, but I don't know. What do you think?
It's pretty good.
You don't need to tell me, but yeah.
No, it's pretty good.
Okay.
I tell you, I like the one in the upper left the best, though. It's
upper left, the Frankenstein one.
Yeah, that's that's the real you.
Yeah, I can put some makeup or spend the night without any sleep, and probably I'll get closer to that. Yeah. Okay.
But look, you know, the interesting thing is how it did get the chin. It got your lips. It got your nose. It got your hair. It just and what screwed it up was your glasses, like you said.
Yes. In fact, the last one with the smile is pretty good, actually.
Okay.
Yeah.
Now, are these online, and we can put our own pictures in and generate these?
Yes, this is on Google Colab. It's a Colab is an online free platform, so you can go to this link, and if you can run it and edit it at the end, you need to upload your picture, and yeah, let me know if you want to do it and you are not. You try with this link, and if you find any trouble there, I can help you to get it done. I can go. If you have never used these tools, when you're familiar with the tool, it seems straightforward, but when it's new, maybe challenging. So I will be happy to help if you want. So there is discriminative models in neural networks that learns to classify inputs into categories, and they map they learn a function that maps the input with the output. So the conditional distribution of what's the probability of one output given the input of the network. These are the classifiers in classifier neural networks are discriminative models. With GANS, we have generative models, and they model the data distribution from a finite amount of samples. And they try to learn the structure of the input data and to generate synthetic data. So they learn the joint probability of the input data and their level. To illustrate how the generative networks work, autoencoders are a good basis, and they can be used as generative models as well. They have an output layer with the same dimensions as the input layer, and the number of units in the hidden layer in the middle is reduced. So they are a lower dimension representation of the same data. The hidden layer is called code or latent variables or latent representations, depending on the context. But it's a short code of the input. And after compressing the input to the hidden layer, the autoencoder the decoder reconstructs or tries to reconstruct the same input. I'm sorry, my screen came black. Here I'm here again, sorry. Yeah, so the autoencoder, the decoder part tries to reconstruct the input from the hidden layer. This part, the decoder part of the autoencoder is what is called a generative model, a generative network. That section of the autoencoder is a generative network. So if we want to use it as the decoder of the autoencoder has the encoder, the code in the middle layer, and then the decoder. It has an input, and it tries to reconstruct the output as close as possible as the input. So if we want to use an autoencoder as a generative model, we can remove the encoder, just input a random vector in the waste, in the code, in the hidden layer, and then the decoder will produce a synthetic image. The quality of autoencoders is usually blurry, as you see here. So this simple approach, you're going to get something, but probably they are not going to be very sharp results. But it's a good reference before analyzing the GANs by itself. Autoencoders can be convolutional too. This is a convolutional autoencoder. The input image has three filters, 3 colors. Then the convolution and with max pooling or striding, they are reduced, the dimension, and then the number of filters is increased. You see that in the volume is the shape of the volume is larger here, and here is even larger because you have less channel. The convolution reduce the dimension, but you add filters too, so you get more features there. For the convolutional layer, they use fractions of strided convolutions, so that way they increase the dimension. Here, we are going to see an example of interpolation. So in order to interpolate between images with the help of autoencoders, the process is to encode different images, in this case a 0 and a 9, with the encoder part of the autoencoder into the hidden layer. This will be set 1 and set 2. And then you can add weight them, these two numbers, these two latent representations, you weight them with a parameter, and then you input that result, set sub alpha, into the hidden layer, and with the decoder you can get an interpolation. This from the 0 to the 9, and you get the values in the middle. That slowly transitions from the initial image, the 0, to the 9 at the end. Autoencoders can also be used to denoise images. The denoising autoencoder tries to undo the effect of noise in the input. So it takes the noisy input, it encodes it, and the output of the decoder, it's going to be another version of the input, but without that noise, that better approaches the original image. The hidden layer, as it is a dimensionally reduced representation, it's forced to learn a general structure of the data instead of every other detail. And here is the scheme of GANS. They have two parts. They have a generator, that is the module that is going to produce the final products once it's trained, and the discriminator. We can compare the generator with the decoder part of the autoencoder when the reconstruction happens, and the discriminator with the encoder part. So the discriminator and generator, they compete against each other in a zero-sum game framework. Here in this reference, generative adversarial nets, this is the first paper published in 2014 by Goodfellow on generative adversarial networks.
So if you could go back, what was the differentiable part there?
Yes.
What does that mean?
Yes, in order to train the discriminator, you have inputs that are real data and fake data coming from the generator. And the discriminator classifies the inputs as real if they come from real data, or fake if they come from the generator. So you can train the discriminator because you know where the images you're training with comes from. So that's your loss function. You get the values to train the discriminator. In order to train the generator, you input the generator with noise from some distribution, and you get an image. And in order to train the generator, you need to know what's the error of your output. And you can do that because you get the value, real or fake, from the discriminator, and that's going to be the loss for the generator. If the discriminator says it's real, then the generator is happy with that, because that's what the generator wants to produce data that looks real. But if the discriminator says it's fake, then the generator knows that it has to improve, it has some loss. And the real fake category is a continuous value between 0 and 1. It's not a 1 or 0, it's just so you can train the generator because you have this differentiable function in the connection with the discriminator. So that's the idea.
By the way, if anybody has any questions, go ahead and go and ask them in real time. How does the discriminator differentiate between real and fake outputs?
The discriminator is a discriminative network, a classifier. So when you train the discriminator, you train it with real data and with data from the generator, and you have the labels for training the discriminator. So once it gets trained, it works as a regular neural network classifier. We are going to go in the next slides to analyze how the training happens.
Okay, so it's more than an encoder, it's a classifier also, right?
Yes, it's something that we can compare with encoder because it takes an input image and it goes down to one value to classify to one dimension. So that's the same shape as the encoder, is something we can compare with. I think it's more accurate, the comparison between the generator and the decoder of the autoencoder in this case, but yeah. It's more like a classifier, the discriminator. So, yeah, go ahead.
I have just a quick question about sort of the noise input.
Yes.
So presumably that's sort of happening in the latent space.
Yes, that's noise. Yes, that's noise that you input with the dimensions of the hidden layer in the latent space, right?
So when you sort of inject that noise, how do you sort of make your model sort of less sensitive to very slight variations in the latent space? Like, for example, if you ever like looked at the latent space of an image through a convolutional autoencoder, there's not really a one-to-one correspondence between like one feature and then one dimension of the latent space. It does really good at sort of packing multiple features into fewer channels. I'm curious, like, are you using a mechanism to sort of decorrelate the latent space?
Well, yeah. There is you have to choose your noise. It can be multivariate Gaussian noise or uniform, and then there are ways, there are variations of the autoencoder, like the variational autoencoder, that actually forces the latent space to learn different features for its neuron of the latent space. You save only the mean and the standard deviation of a number of features, and you force the structure to learn different features. So yeah, there are a number of ways, and it's still an open field of research. There is even GANs that work against to produce a good distribution for the latent space for autoencoders, actually. So sometimes you can use GANs to produce a better distribution in the latent space of an autoencoder. So that's a very good question. So I have some ideas to answer, but I don't know if that helps.
Well, I think let me give an answer, and Glauco, you can give a thumbs up or a thumbs down. I don't think in the vanilla generic presentation that Glauco is giving that there's any attempt to establish the correlation between the inputs and the outputs in the latent space. We just know that there's a relationship there, and we can find out if it's a good relationship by seeing if the latent layer generates something which is classifiable, but that's really all we know. I don't think there's any direct comparison. Is that correct? Is that correct, Glauco?
That's correct. If we are successful in this scheme of generative adversarial network, there should be a correlation between the distribution in the latent space and the real images and the transitions that will be the perfect scenario. But yeah, with a vanilla and generative adversarial network, probably that's not going to be the case. You have to. There are more additional works to the scheme. This is the basics of the relation between generator and discriminator. But then there are a lot of little, little improvements that has to be done in order to be successful. Yeah. There are any other questions? Okay. So the generator generates new data, and the discriminator evaluates if the new data is authentic or not. Here I wrote that set is random noise and can be viewed as the latent representation of the data. Yeah, it can be if things are perfect. If not, yeah, as we analyzed before, it's not going to be to correspond that nicely. So the generator maps the sample, the latent prior of that noise in set. It maps it to the sample space of the data distribution, that X. So the generator defines a distribution for the model given the inputs and the parameters of the network. And then the discriminator tells how real the sample is via a score, a real number between 0 and 1. So that's the probability that the input comes from the data distribution rather than from the generator model. You can train GANs with images. In this case, the discriminator is a convolutional binomial neural network, binomial classifier, and the generator is the convolutional neural network.
So the discriminator, you have it here, is trained as a classifier.
Yes, that's generally the case. It classifies. It's a binary classifier, a binomial classifier. That's generally the case. We will see another models with that they have more outputs, but they always have this output, real or fake. That's always present. Yes.
Thank you.
And the objective of the discriminator and the generator are contrary to each other. The losses of one push against the losses of the other. If you have a good discriminator, the generator is going to have more loss. And if you have a good generator, the discriminator is going to increase its loss because they push against each other. So with images, the generator takes random noise and produces an image, and the synthetic image is fed to the discriminator with real images from the data set. So the discriminator takes real data and synthetic images and returns probability between 0 and 1, and 1 represents authenticity and 0 represents fake. Here there are some examples of GANs. This blank does not exist, so we can go with person, cats, horses, chemicals, artworks. So I don't know, we can do persons.
No, do cat, because I think we've gone through this person does not exist. But okay,
you have gone through it. Okay, this is, you already know that one. Okay.
No, but go ahead. Here's the funny part. When you do this long enough, you get monsters in the upper left-hand corner. I don't know if you've ever seen that.
Yeah.
There it is. Stop there. See that little fleshy appendage on the left?
Oh, on the left. Yeah, that's a big one.
Yeah. So what you do is this one kind of screws up. And sometimes you get this half of a face of a monster, just looks like a total mutant on the left.
Yes.
Now, can they clear that up? I imagine they probably could, but they didn't do that here. That's very interesting, I think.
Yeah. They also get these little blobs that are more common even than the monsters. These
Ooh.
and these are very troubling.
She has a beetle in her hair.
Yeah, that's very common. They
A
appear
Japanese beetle.
in different places.
Really?
I can go with cats because you already saw the
Okay.
the faces. So these are fake cats. These are not real cats. Yeah. And what else? The horses, they are not very good at all. So I can show you the horses. This is not that good. They are like
Three-legged horses. I see a three-legged horse there.
yeah. I don't see the head here. There is a cat in the middle. So sometimes you get weird. This is a good one.
Ah.
But yeah, neural networks are probabilistic, so there is always a chance to get it wrong. And
I want to see chemical. What kind of chemical doesn't exist?
I have no idea. They put chemicals here, and you can put your mouse, your cursor on them, and they explain what is each thing: the bond, the atom, the molecule. They have different three-dimensional shapes. Probably for experts, these chemicals are significant, but for me, I cannot tell.
So these are real chemicals with no known use, no apparent use, unless you're an expert and you recognize them.
Yeah, at least they are not for real. They don't exist. So I don't know what to do with them.
I don't know much about chemistry, but those look like really righteous molecules.
Yeah, probably.
You know,
probably
the carbon, I recognize the carbon and the helium bonds, and I have no idea if they're real or not. Anybody have enough chemistry to comment?
Yeah, this one seems less impressive because you could make this with a random number generator.
Oh, really?
Okay.
Yeah, because you know carbon has 4 bonds, nitrogen has 3 bonds, oxygen has 2 bonds, hydrogen has 1 bond. So if you had someone with enough domain expertise in a random number generator, they could make a chemical. So the other ones are more impressive than this, I would say.
I see.
Okay.
Okay. Let's go through the artwork. I think that's a fun one. This is supposed to be art. This is not that impressive. There are better examples. Yeah, they are like. If they don't tell me that they are fake, I could even pay for some of them.
They look like children's finger paintings in some cases.
Yeah.
That looks like my big toe.
Yeah.
Okay.
I cannot go back. I just keep refreshing the page. Yeah, these are some examples of what GANs can do.
Thank you. That's fascinating. I think I mentioned in here the difficulty of differentiating whether art is art or whether it's garbage. And I maintain that art goes back to the creator. And you have to have some relationship with the artist in order to appreciate art. And have I given the example of like Whistler's mother in here? Okay. Okay. Here's the idea. You have Whistler's Mother, which is a very famous painting, made famous in the last Mr. Bean movie.
Yes, I remember that.
You watched the Mr. Bean movie. Okay. Imagine making a duplicate of that painting molecule by molecule. So it's totally undifferentiable from the original. But on the back of the original, you put a little plate said original, and on the copy, you put a little plate on the back, which is the copy. Which one do you think would auction off with a higher price at Sotheby's if they were put under auction, one after the other? I think it's obvious the original would. The original would because it goes back, it has a history to Whistler. Yet the other one, which is molecule by molecule, exactly the same, would be recognized as a copy and that copy could have other copies. And it relates back to the copy, but it does not relate back to the original, which relates back to Whistler and his mommy. At least I think that's the case. So art has a lot to do with identification with the performer.
Yes.
So I don't know if anybody saw the movie Yesterday. It was a story about there was this meteor that hit the earth, and everybody except this one nightclub singer forgot all of the songs of the Beatles. So he came on, and the name of the movie is Yesterday. No, I don't particularly recommend it, but he remembered all of the songs of the Beatles. And what he did is he came out and he released like Yesterday and I Want to Hold Your Hand and Sgt. Pepper's Lonely Hearts Club Band. And they all became these enormous hits. That whole movie was built on the premise that the songs alone were the cause of their popularity. They weren't. The Beatles came in. I'm old enough. I've been to two Beatles. No, I've been to one Beatles concert. I went to a Beatles concert. Yes, I'm that old. At Municipal Stadium in Cleveland, and we couldn't hear them play. All the girls were screaming so loud that our eardrums met in the middle. But they came through. They had all of this hype associated with them. They had the strange haircuts. Everybody at the time was wearing something called Beatle boots. Everybody was, which was kind of high heels, but not really high heels, more like Cuban heels. And everybody was trying to emulate the Beatles, and that's where long hair came from in the 1960s. And their music became popular because they were on a platform that allowed their music to have visibility. And I maintain that if you took away that platform and that visibility, that the songs of the Beatles would be, they're good songs. I mean, there's a lot of songs that are really good. I also maintain there's probably a lot of songwriters in Nashville, Tennessee that can write songs as good as the Beatles, but they don't have that platform. They don't have that foundation of their history on which to build. So, judging art is really, really rough. And, just judging art by, here's AI art, and you don't have anything to relate it to. And I think that diminishes from the quality of it, as opposed to, for example, a Jackson Pollock picture or painting, where he was a guy that took and he splashed paint all over canvases and stuff and sold it as art. At least there you have a relationship with the artist. So that's my 2 cents on assessing the value of art, be it painting or music, that you have to relate to the artist in order to, and the history of it, in order to give it value. Anybody want to push back on me? This is totally heuristic. This is not math. This is not science. This is not engineering, but I think
I will say that it's difficult to relate yourself with the programmer of the AI.
Yeah.
Like too far away from you, so it doesn't mean anything to you. It's like, yeah, a computer program, I don't care. Nobody cares.
There was this painting made by AI that sold at Sotheby's for $500,000, almost $500,000. And everybody said, great. So they used AI to generate a bunch of other paintings. None of them sold. The first one sold simply because it was the novelty of the first painting to be generated by AI. So it had very little to do with the art and much more to do with the novelty of the piece, in my opinion. Okay, that's enough of my pontificating about originality here.
Okay, so let's continue with how do we train generative adversarial networks. So the goal is to find the parameters for the generator that makes the data to look like the training data to the discriminator. The discriminator training backpropagates from the binary classification loss, and the generator training backpropagates from the negation of the binary classification loss of the discriminator.
Notice that we just went over the algorithm of error backpropagation. It's everywhere, including here.
Yeah. So the parameters of the generator and the discriminator, they update alternatively.
Could you define the variables here, theta G, theta D?
Yeah, these are the parameters of the generator, and these are the parameters of the discriminator.
Okay, thank you.
So yeah, that means that the training process, it trains one run through the discriminator, one run to the generator. It tries the process of training that's for balancing how they learn. So they keep learning at the same speed. So if one of them gets very well trained and the other doesn't, it's going to be difficult to match them back together. So there is a difficult training process there to keep it going well. So the discriminator is a neural network with one output between 0 and 1 with the probability of whether the input is real. If the probability is 1, it means that the example is real, and if it's 0, it means that the example is fake. And the goal of the discriminator is to classify correctly the real examples with a level of 1 and with a level of 0, the synthetically generated examples. The generator takes noise from the dimensions of the lattice space as input and use them to generate examples with the dimensions of the data. The error of the discriminator is used to train the generator, so we can create with the train generator samples that looks like coming from the real data distribution. And the objective of the generator is to generate examples that can fool the discriminator. So being fake, but they fake examples, but the discriminator levels as 1 as being real. So the objective function of the discriminator is this here, where this part of the equation, R stands for the real samples and S for the synthetic samples. So let's say that the discriminator if the discriminator says that X is if X is real, and the discriminator labels it as real as a 1, the log is 0, and if the discriminator labels the synthetic samples as 0, then the loss is 0 here as well, so the loss function is 0. If you go apart from that, you go to minus infinity, so that's smaller than 0 in any case. So we want to maximize the loss function, the objective function of the discriminator, so it gets closer to 0. That's the goal. Whereas the objective function of the generator, it only uses the synthetic samples, and it takes the classification of the value, the score of the discriminator. If the discriminator assigns a value of 1 to the fake sample, the loss function will be 0, so the loss function will be 1. Whereas if the discriminator assigns a value of 0, let me start again. If the discriminator says it's real, then we have 0 here, and J is minus infinity. Whereas if the discriminator says that it's fake, we have a 0 here, so this has a value of 0. So we want to minimize this, because if it's 0, the generator is failing, but if it goes to minus infinity, the generator is doing great.
Now, D takes on a value between 0 and 1, right?
Right.
So if you remember this, taking the log of a probability as information. So we are actually maximizing a type of information here.
So this should be this is the cross entropy loss as well, right?
The
I don't
cross
think-
entropy.
No, I don't
Yeah,
see any,
no.
I don't see any
I-
cross going on here.
No, it's not the cross entropy. The cross entropy is for the classification, right? You use for classification. Yeah, no, this is for this. This is a different function, actually. Yeah. So for the parameters of the discriminator, we use gradient ascent because we want to maximize the loss function. And for the generator, we use gradient descent because we want to minimize it. The gradient update steps are alternated between generator and discriminator. And in this iterative process, we train a little bit more the discriminator in k steps for each step of the generator. So the discriminator keeps near the optimal solution while the generator changes slowly. With a number of times like k equals to 4, for instance, we take a mini batch of size 2m for training the discriminator. And it's 2m because it has the equal number of real samples and synthetic samples. Then stochastic gradient ascent is performed for the discriminator to maximize the likelihood that the discriminator correctly classifies both the real and the synthetic samples. And for each update step, with the backpropagation is performed on the discriminator network with respect to that mini batch of 2m real and synthetic examples. In the generator, we only use M because we only use noise inputs. We don't use real data to train the generator. So with M noise inputs, M synthetic samples are created, a mini batch, and the stochastic gradient descent is performed on the parameters of the generator to minimize the likelihood that the discriminator correctly classifies the synthetic samples. So the discriminator and generator are connected to each other, but when we train the generator, only the weights of the generator are updated, not the weights of the discriminator. The iterative process is repeated to convergence until Nash equilibrium. Nash equilibrium is in games when there is an equilibrium and when one of the agents change a little bit, it doesn't improves their position, neither of them. So they keep in game theory, they reach equilibrium. Yeah, that's what it means. And at that point, the discriminator is not able to distinguish between the real and synthetic examples. The generator may produce burst samples in early iterations. So we can train the generator to maximize the log of, to maximize to maximize the result of the discriminator instead of negating it. So that means that we go from 0. We start with this loss, with this. With maximizing this goes from 0 and up to 1, instead of going from 0 down to minus infinity. So the range is much smaller, so subtle variations are easier to identify during the training. So
I will mention, I always like historical stuff. And the Nash equilibrium was named after John Nash. John Nash. If anybody of you has ever seen the movie A Beautiful Mind starring Russell Crowe, it's a story about Russell Crowe starring as John Nash. He had a lot of mental problems, but was a mathematical genius. And he was the one that came up with this idea of the Nash equilibrium, which nobody had ever thought of before, and ended up winning a Nobel Prize in economics because of that. It turns out that businesses need to work to get to a Nash equilibrium so that all of them thrive and prosper as well as they possibly can. So that's what we're aiming for here in this Nash equilibrium.
Thank you. So big problems with GANs is that they are difficult to convert, some large problems, and that Nash equilibrium does not happen in practice, actually, and it's rare to get. Yeah, that's a big problem. And some failures are that the discriminator becomes too strong too quickly, so the generator cannot learn anything because it cannot fool the discriminator at all because it's very good. Multicollapse is when the generator learns only a very small subset of the true data distribution, and it keeps producing the same, whatever noise you input, the generator produce the same kind of images or input samples. So it's not the goal. The goal is to have to model the actual data distribution, not only a portion of it. Then the vanishing exploding gradients from the discriminator to the generator. If the generator is trying to learn from the output of the discriminator, so if the variations on the generator produce very small variations on the discriminator or too big, it's going to be difficult to keep the training going. And it can also happen that the generator learns some weaknesses of the discriminator. So it learns, if I put this pixel here as black, it's going to classify the image always as real. And the discriminator don't care about doing anything else. Just that's an example of some weakness of that the discriminator may have, or whatever other one. I included this. There are ways to work around to solve these problems to minimize that risk. One example is packing, and it's to prevent the generator from producing always samples of the same kind. So packing consists of modifying the discriminator. So instead of making decisions as real or fake from one instance for each instance, the decision is made based of multiple samples from the same class. So that way, naturally forces favors the generator to produce distribution with more variation, with less multicollapse. Okay. This is one example. Okay, there are other structures for GANs. Conditional GANs include other information in addition to the noise that is input to the generator and also to the discriminator. So depending on in this picture, depending on the class that you input to the generator with the noise, the generator learns to produce different kind of outputs, and the discriminator also has that information. So if the generator did it correctly, the discriminator will know that it was fake because it will then correspond with the class. This is an example of conditional GANs, for instance, with street scenes. So each part of the picture has a label on it, like this is a car, this is a light, this is a tree, this is the sky, this is the road. So then the output of the GAN generates for each part of the image a different element, the tree or the car, depending on the class that is input with the law. The same with facades.
Facade.
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 Okay.
I know France borders Spain, but it's facade. Yeah.
Facade.
Okay.
Yeah, facade. It's very similar to the Spanish word.
Oh, is it?
A false friend between French and Spanish, probably. Okay, so aerial maps and day to night, or edge just to photos. Another variation of GANS is an auxiliary classifier. So the discriminator learns to differentiate between real and fake, and also to classify to the class of the input. So the generator has to learn to do the same thing. And this is an example where a gang is, so these are the original pictures. So this is from the description of this picture. The flower has yellow petals along with green and yellow stamen. So this text is input to the gang alongside with an input vector noise. So from this text and from the noise, the GAN generates different instances that corresponds to this description. And these are different examples. These are amazing for me. It's like, wow. I think about replicating some of this stuff, but that brings another problem, like the computational resources that has to be addressed very careful. You were going to say something, Dr. Marx?
No, I was inhaling deeply.
Okay.
I wonder how many of these were cherry picked, whether these were generated consistently or whether they generated 4 or 5 and chose a good one.
Well, yeah,
it's hard to tell. You always get, if it isn't operating 100%, you get the cherry picked ones. So
yes,
it was just
definitely.
a thought I had. So probably not applicable here because it's unknowable. We don't have enough information about this.
Oh, sorry. Yeah, no, we don't know. Yeah. I cannot answer to that question. That's something to check and implement it by ourselves and check that it works. So yeah, this is another application of GANS for super resolution. Here in the image, all the pictures are the same size, but the original image will be smaller and the super resolution GAN will be larger. So this is a comparison with other techniques for super resolution, and the GAN is very good actually. So we still have some time, Dr. Marx. What time is, like 15 minutes, right?
Yeah. I have some comments and questions. Do you have any more, or this?
I have some more. I have like 5 more.
Oh, please go
Okay.
ahead. This is just fascinating.
Okay. This is cycle GAN.
Yeah, if you could go back to the previous one.
Okay.
I don't know if any of you have ever seen cop shows where they show a blurred photograph of the police are chasing somebody, and they showed a blurred version of a license plate.
Yes.
And the cop comes up to the technician. He says, "Johnny, sharpen it." And you see this little click, 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 and the fuzzy thing becomes totally clear. Have you seen that on TV? Any of you?
Yes.
That sort of thing. First of all, I don't think that is possible unless you know something about what you're trying to restore. But maybe, just maybe, if you restrict yourself to restoring license plates, maybe you can do something like that with the technology which is shown here. In other words, if you restrict yourself just to license plates, maybe that stuff on the TV that we see where he says, "Johnny, sharpen it," click, 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 and you get the license plates exactly, might be possible. So I can see a technology like this, again, focusing on license plates with the learning set being license plates, maybe doing something like that. I don't know.
Yes, it sounds like totally possible. Like, yeah.
Yeah, let's go into business.
Like a good project to
yeah.
Okay,
go ahead.
This is a cycle GANS. It takes 2 image collections that they are not necessarily paired image to image, and the algorithm learns to translate from one collection to the other. So these are the examples from photos to Monet pictures, from zebras to horses, and vice versa, and from horses to zebras, from summer to winter and winter to summer, and from a photograph to different styles. These are more
Go back to the previous one.
Yeah.
Look at that Van Gogh, and I've heard of Monet and Van Gogh. I haven't heard of these other two, but
Me neither.
That's frankly astonishing, isn't it? Isn't that something?
Yeah, yeah. And the very interesting thing is that the algorithm learns it even if you don't have in pairs, because if you have pairs of pictures that corresponds exactly the same shapes, and you go from zebras to horse, but you have a lot of training data that are exactly the same picture as a zebra, exactly the same shape as a horse. Okay, that's something kind of easier to grasp, but there is no need for them to be paired. You just give collections, and the algorithm learns to translate between them. I think that's amazing.
Okay, great. Thank you.
These are from apples to oranges too, and vice versa.
That's funny. Familiar with the old saying, comparing apples to oranges? Well, I guess you can. Okay, good.
Okay. Yeah. And these are more photos to paintings, the same as before, more detail. And next thing, paintings to photos too. The input is a painting, and you get a photo from that painting, and from a painting, and you get the photo. Yeah. Okay. Regarding the style, the GANs that generate these faces in high resolution with that level of detail, they do a number of techniques. They include a number of techniques, but this one that they also use is very interesting, and they do the next thing. So they start with a generator and a discriminator that they have only 4x4 pixels. So before they train the GAN for 4 pixels, for 16 pixels, I mean, and once they get it trained, they increase the resolution to 8x8, and they train again. And they keep going in powers of 2 till they get to the final resolution. And that intuitively explains to us how this is working with such a level of fine-grained detail in the images that is amazing. And if you, for instance, in this image, you see here a blob, like a gray thing.
Yes.
Sometimes these little defects usually they start from they are defects that are carried to the final results from the smallest resolutions. So they start appearing here, and they get them projected to the picture at the end. So yeah, those are things that they are still working on. I think this is the second or the third version. I think they are in the third version already of the style GAN. But I think this is very interesting, and this strategy of going from lower resolution to higher resolution. And then
so if we could go back, I want to make sure I understand this, because I haven't seen this before. So first they do some training on 4x4s, is that right?
Yes, they take the training data set, they convert it to this low resolution, and they train the generator and the discriminator
on the low resolution, and then
low resolution.
They augment the neural network. They take a different neural network and train that at a higher resolution.
They keep the training for that low resolution, but they add more layers, both in the generator and the discriminator, to increase that resolution. So this 4x4 here is the same as before, the previous weights, but they make it's a different network, yeah, but it's like they transfer learning somehow to part of the.
Okay, understood. Yes.
Okay. Any other questions? No. Okay. So this is how long it takes to train this kind of GANs with that good results. At Baylor, at Kodiak, we have a supercomputer that, and we have this kind of GPUs, Tesla V100. They are like on the tens of thousands of dollars for each server. And they have, I don't know if they have maybe 4 or 8. We can use one of them or maybe 2 in the same server at the same time. But programming for parallel computing is, yeah, we could get to this like a couple of weeks to get something working on this. But it's very demanding. You need to know what you are doing because you cannot iterate that much. You start training for 2 weeks and then, oh, this didn't work. I'm going to try another thing.
I left out a comma, yeah, or something.
Yeah. But yeah, I think this is interesting to know. And this is another application of GANs. They input voice and they get images of people. And look how accurate it is. Like from the voice, we can play the samples here. You cannot listen then.
Okay, can I suggest something?
Yes.
What I want you to do is to unshare your screen. And then there's a process where if you share your screen, if you go down to the bottom left, hit the share screen button, and down in the bottom left, it says share video or share audio or something.
Share sound. So let's try now.
Yes. Okay, good.
There'll be someone after
Is working?
Yes.
me, and so hopefully someone after them again. So it's there'll be someone after me.
So from the audio, they get the image, and this is the original image for reference. So look how accurate it is. They don't use the image to generate this reconstruction. They only use the voice. This has very ethical considerations, but anyhow.
And they couldn't prove that Fang was Sherwood Diller because I never meant for it.
It's too loud for me. I can play some others.
I think, the frame of it, they're just gonna walk out and it was just a great adventure movie.
I think this is so intriguing because if they take my voice, they can know how I look like. So that's.
I tell you, this result is hard to trust.
Yeah, okay.
I wish I could dig deeper and understand it, but this looks too good to be true. But man, if this were true, I don't see how eye color relates to voice or skin color. Well, I don't know.
I wanted to try this by myself and record my voice and get the output and see it was my face. I think they have this is the GitHub. So I thought the code was going to be here, but I don't think I have found the source
You
code.
found it. I bet you if you put in your voice, you get that Frankenstein guy back.
Yeah, you're right. It's not easy to trust it.
Okay.
I would like to test it for real by myself. Actually.
Yes. Okay.
And I think that's all I have.
Okay. Thank you, Glauco. That was fascinating. Let's give Glauco a hand. So we're all muted, so you have to run this through a video picture and then output the applause using a GAN. Here's the way that I get the overall idea of a GAN, a vanilla GAN, okay? If you have, for example, a bunch of pictures of faces, and you think of the space of all images, so you have the space of all images, you have noise, you have pictures of your Uncle Jimmy, your Uncle Basil, you have pictures of toe fungus, of cucumbers, of anything that you can imagine, okay? That's a humongous space, right? It's just humongous. Now, what you do is you give it pictures of faces. Now, those pictures of faces in that humongous space dictates, well, there's a face here, 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 a face here. But the problem is that space is so incredibly large that you can't pack examples in there. But by those examples, you have identified a portion of space, okay? What the GAN does is after that portion of space is identified, it begins to pick additional elements within that subspace, if you will. Ooh, there's an element here. There's an element here. Ooh, there's a face here. There's a face here. And in the GAN, it inputs something and says, oh, nope, that's not a face. Ignore that. Oh, that's not a face. Ignore that. Oop, that's a face. That's a face. Add that, add that, add that. Oops, that's not a face. And pretty soon you begin to pack the subspace with other pictures of faces. And that is my understanding of the vanilla, the basic idea of the GAN, is that's what it's doing. Do you agree with that assessment, Glauco?
Yes, I think so. I think so. And it's very, the question that Colin asked before about the distributions from your noise to map it to the distribution of your data. I think that's, yeah, that space of that distribution of the faces, for instance, in the high dimensions is very complex to, to geometrically analyze at all. But that's the idea, to map everything that comes out from the GAN, from your latent distribution, whatever distribution you want to choose, to that space, to that distribution of the faces space. That is humongous, is so complex that I cannot imagine it geometrically. I don't think anybody can. But yeah, it seems to get it's working somehow, not to perfection. I don't think it's going to go.
Yeah, it's filling in that subset of spaces that are also faces. So that's at least my interpretation of the generic vanilla, if you will, GAN, in terms of what's happening. The challenge here is that we're used to thinking of Euclidean spaces where you measure the distance using some sort of metric like a root mean square or something like that. I'm currently thinking that you can't measure it using a root mean square, that you need some sort of other metric, and how you measure it, I think, is still an open question. That would be nice to know. Okay, are there any final questions for Glauco or me?
Yeah, can I sneak in a question? This is kind of for both Glauco and Dr. Marks. I was curious, have you read the Wasserstein GAN paper that talks about the use of the Wasserstein distance?
Well, this is something that came up on Justin Bowie's PhD examination. If you look at neural networks, there is over a paper published every 5 minutes in the area of artificial intelligence. So keeping up with the literature is something which is impossible, but it's always nice to have a filter. So the answer on my side, I suspect Glauco's, is no, that we haven't.
No, I have looked to it. I know that.
Oh, you have? You're a prolific reader. That's pretty good.
because I was preparing this presentation. I was present at Austin's dissertation, so I say, oh, that's interesting. So I look at it just recently, and it helps to. My takeaway is that it helps to.
Could you summarize it first before you give the takeaway? What's it doing?
Well, I cannot summarize it. I'm sorry.
Okay, go ahead.
I cannot do that. Maybe Colin, you can.
Yeah, like I skimmed through it as part of my work actually this past summer. But basically, like the loss metric that Glauco showed, it has one of the properties it doesn't satisfy is the triangle inequality. Whereas there's another, it's sort of a loss metric. It's technically a metric, whereas like the cross entropy, for example, is not a metric. It doesn't obey the triangle inequality. This is the Wasserstein metric is basically like, you imagine probabilities like piles of dirt. It's the amount of work you need to do to move one probability distribution into another. And because it obeys the triangle inequality, it like mitigates certain things like basically, at least mathematically, you can show that it prevents mode collapse, which is pretty fascinating.
Okay, we need to define mode collapse, which we haven't defined in here yet.
Yeah, that was my takeaway. Mode collapse is when the GAN learns only a subspace of the data distribution. So the WGAN helps to avoid that somehow. So
In other words,
Have it-
avoids learning just a narrow piece of that subspace.
Yes, yes, and it's actually available in TensorFlow, the implementation. You can use it. So it's kind of state of the art.
And why do you want to avoid mode collapse? It seems that as long as it collapsed within the subset, that would be okay. I guess it's the way you define it.
Yeah. It depends on how much it collapses, I guess. If you only get always the same face of the same person or the same family of people, you want
Right, you get
to
the same
cover
thing.
the whole humanity, right, with your GAN.
So that's bad, of course. So you want to spread out the glory, right?
Yeah.
Okay. Any other final questions? Okay, thanks everybody. We'll see you next time when we will have Justin Bowie present some of the resources that are available. And you need to pay attention to this because I'm going to ask you to do something as a class project. And then after that, we will start looking into the what you found out about the active information of tic-tac-toe. Okay. Thank you. Bye-bye.